Welcome to Yashil Chemistry Academy, Lecture 2. Today, we'll be seeing the Henry's Law, application of Henry's Law, and numerical based on Henry's Law. Let us start. Henry's Law. Basically, we discuss about the solubility of a gas in a liquid. Solubility of a gas in a liquid is a exothermic process. In 11th standard, you studied that the exothermic reactions are not favorable at a higher temperature. Therefore, solubility of a gas in a solvent decreases as the temperature increases. Whereas solubility of the gas in a solvent increases with the increase in pressure. As the pressure increases, solubility of a gas in a liquid will increase. As the temperature increases, solubility of a gas in a liquid will decrease. Now let us see the relationship between the solubility of the gas and the pressure applied above the solution. It is given by Henry's law. There are two ways of expressing Henry's law here, or stating Henry's law. First one is at constant temperature. With the increase in at constant temperature, solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the solution. At constant temperature, solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the solution. P is the partial pressure of the gas is equal to Kh, called as Henry's law constant, into mole fraction of the gas. Mole fraction is considered as solubility here. Mole fraction is considered as solubility. Therefore, you can say at constant temperature, solubility of a gas in the liquid is directly proportional to the partial pressure of the gas above the solution. Another way is, instead of using solubility, I can use the term mole fraction here. Mole fraction of the gas in a solution is directly proportional to the partial pressure of the gas above the solution. Mole fraction of a gas in a solution is directly proportional to the partial pressure of the gas above the solution. Of course, temperature should be maintained constant. Kh is called as Henry's law constant. Okay. Kh is known as Henry's law constant. So there are two ways of expressing Henry's law. P is equal to, that is partial pressure of the gas that we are going to apply above the solution, equal to Kh, Henry's law constant. It depends on temperature, into mole fraction of the gas, a mole fraction of the gas present in the solution. Okay, let us say at constant pressure, given pressure, I'm taking a particular pressure and comparing the solubility of the gas here, right? So here P equal to Kh into Henry's law constant into mole fraction of the gas here. When the Kh value is higher, solubility becomes lesser here. Higher the value of Kh, lesser is the solubility of a gas in the liquid here. Kh is higher, lesser will be the solubility of a gas in the liquid here. Again, Kh also depends on temperature. Kh depends on temperature. As the temperature increases, value of Kh will increase. As the temperature increases, value of Kh will increase. Therefore, the solubility of a gas will decrease with the increase in temperature. That is the reason why aquatic life are more comfortable in cold water than in warm water. Reason is solubility of the gas decreases with the increase in temperature. This type of statement we can expect from assertion reasoning question. Assertion, they will give aquatic species are more comfortable in cold water than in warm water. And then reason, they will give some reason. Solubility of gas decreases with the increase in temperature. Or sometimes they give solubility of gas increases with the increase in temperature. So you have to find out first, you take it as assertion separately, reasoning separately. Make a tick. Assertion is right, reason is right, and both are related to each other. Or sometimes assertion may be wrong, sometimes reason may be wrong, or assertion, reason may be right, but they are not related to each other. Based on this, you have to choose, give you a choice. Right? So this is the graph drawn, partial pressure and mole fraction of HCl. So you can see as the pressure increases, mole fraction increases. In other words, you can say as the partial pressure, the pressure applied on the solution increases, solubility of the gas has increased here, right? So P equal to Kh, that is Henry's law constant into mole fraction of the gas. Mole fraction of the gas is nothing but number of moles of gas divided by number of moles of gas plus number of moles of solvent. When the Ng, number of moles of gas, is very less, then I can take Ng, number of moles of gas plus number of moles of solvent is equal to number of moles of solvent. In that case, I can write Kh into number of moles of gas divided by number of moles of solvent here. That is mass of the gas, Kh into mass of the gas divided by molecular mass of the gas into molecular mass of solvent divided by mass of solvent, depending on the value of kH on the pressure applied. We decide where we have to take Ng plus N solvent. Number of moles of gas plus number of moles of solvent is equal to number of moles of solvent here. Right. Now let us see at a given pressure, we have seen higher the value of kH, lower is the solubility of the gas here. I have taken three gases here, oxygen, nitrogen, helium. Helium kH value is 144.97 kilobar. Oxygen 34.86 kilobar. Nitrogen 76.48 kilobar. So helium has got the maximum kH value. So it has got the least solubility. And then oxygen has got the minimum kH value. Among three gases, minimum kH value. So you can say oxygen is most soluble in water when compared to helium and nitrogen. So solubility helium less than nitrogen less than oxygen here. So higher the value of kH, lesser is the solubility. Sometimes they'll give you the kH value. They'll ask you to compare the solubility. One word multiple choice question we can get here. They give the value and then give solubility of helium less than nitrogen less than oxygen. And they give different combination. You have to find out which is correct here. There's a graph solubility versus partial pressure. Here you can see helium minimum solubility. Then nitrogen higher solubility. Oxygen still higher solubility. Again, solubility increases as the partial pressure increases. Right. Now let us see some of the application of Henry's law. Gases dissolves in a solvent, let us say in water, at high pressure and low temperature. High pressure and low temperature. That is the reason why soda water is made by dissolving carbon dioxide in water. Here, it is carried out at a high pressure. Higher pressure, it is packed in a bottle at a higher pressure. Solubility of carbon dioxide in soda water is increased by dissolving the gas at higher pressure. Next, we will see when we go deep in the sea here. See, normally swimmers, they go deep in the sea. Scuba divers, they go deep in the sea here. When you go deeper and deeper, the pressure will increase. When the pressure increases, what happens? Solubility of the gas will increase. Pressure increases, solubility of the gas will increase. Right? So what will happen? More nitrogen will dissolve in the blood. More nitrogen will dissolve in the blood here. So when after completing the diving, etc., they come to the surface here. They come to the surface, the pressure will decrease. When the pressure decreases, solubility will decrease. The pressure is decreasing, solubility will decrease. So what will happen? The excess of nitrogen, it will form bubbles of nitrogen gas will be formed in the blood here. The blood bubbles of nitrogen gas will be formed here. This will block the capillaries. When the capillaries are blocked, we get a pain called bend here. You get a pain here that's called as bend here. So that is one of the applications of Henry's law. So we have to reduce the concentration of N2 gas in the air. We have to reduce the concentration of N2 gas in the air. So scuba divers use tank containing a mixture of 11.7% helium. So some helium is added here. 56.2% nitrogen and 32.1% oxygen here. Right. So nitrogen percentages decrease here. Normally air contains 79% by mass of nitrogen. Here it is 56.2% nitrogen percent here. Helium, of course, the solubility is very less. So I'm adding helium in place of nitrogen. Some nitrogen is replaced by helium here. 11.7% helium, 56.2% nitrogen, and 32.1% oxygen here. So this is the application of Henry's law. Now let us say when you go higher up in the higher altitude, say when you are climbing the mountain, partial pressure of the gas will decrease. The pressure of the gas is going to decrease. So what happens? Solubility of oxygen will decrease. So solubility of oxygen decreases, amount of oxygen in the blood will decrease. That is, low blood concentration of oxygen in the blood will be there. So when the oxygen availability becomes lesser, we become weak and unable to think clearly. Our thinking is affected here. These symptoms are called as anoxia. These symptoms are known as anoxia. So these are some of the applications of Henry's law. Now let us see numerical based on Henry's law. Partial pressure of the gas is equal to kH into mole fraction of the gas. That is kH into number of moles of gas divided by number of moles of gas plus number of moles of solvent. In some cases, number of moles of gas plus number of moles of solvent can be taken as number of moles of solvent. First question. How many millimoles of N2 gas would dissolve in 1 liter of water at 293 Kelvin? Pressure exerted by N2 gas is 0.987 bar. KH value for N2 is 76.4 kilobar. That is 76.4 into 10 power 3 bar here. Very high value of KH here. So I written partial pressure of nitrogen is equal to KH into number of moles of nitrogen plus number of moles of water. Number of moles of water is 1000 by 80 because 1 liter of water, density of water is 1 gram per centimeter cube. So 55.56 is the number of moles of water. So number of moles of nitrogen is very less when compared to number of moles of water. So I can take it as partial pressure of nitrogen equal to Kh into number of moles of nitrogen divided by number of moles of water. Right. So 0.987 equal to Kh value is 76.4 kilobar converted into bar into 10 power 3 into number of moles of nitrogen divided by 55.56. By calculating, I get 0.717 into 10 power minus 3 moles here. But here the answer asked here is in millimoles. So multiply by 1000. 0.717 into 10 power minus 3 into 10 power 3. That is 0.717 millimoles of nitrogen is present here. Next is partial pressure of ethane over a saturated solution containing 6.56 into 10 power minus 2 gram of ethane is 1 bar here. What will be the partial pressure of the gas if it contains 5 into 10 power minus 2 grams of ethane? So here the grams is decreasing. What will be the pressure here? There is an inverse proportionality between the amount of gas present and the pressure. Yeah, you just see, sorry, so there's a direct proportionality between the amount of gas present and the pressure here. You'll just see partial pressure of gas is proportional to the mass of the gas dissolved. That is directly proportional here. As the partial pressure increases, mole fraction will increase, number of moles of gas will increase, so the mass is going to increase here, right? At 1 bar pressure, 6.56 into 10 power minus 2 grams of ethane exerted pressure of 1 bar here. Then we have to find out what will be the pressure exerted when 5 into 10 power minus 2 grams of ethane is dissolved here. So you can divide one by the other. 1 by P is equal to 6.56 into 10 power minus 2 by 5 into 10 power minus 2. So pressure is equal to 5 into 10 power minus 2 by 6.5 into 10 power minus 2, which is 0.769 bar. We'll once again see when the gas dissolved is 6.56 into 10 power minus 2 grams, pressure exerted is 1 bar. What will be the partial pressure of the gas if it contains 5 into 10 power minus 2 grams of ethane? So partial pressure and mole fraction directly proportional. Therefore, we can say partial pressure and mass of the gas is directly proportional here. So 6.56 into 10 power minus 2 grams exerted pressure of 1 bar. So 1 bar is proportional to 6.56 into 10 power minus 2. 5 into 10 power minus 2, what is the pressure we have to find out? So divide one by the other. 1 by P equal to 6.56 into 10 power minus 2 divided by 5 into 10 power minus 2. So I can find out the pressure, which is equal to 0.769 bars. Solubility of H2, standard question. H2S in water is 0.195 mole at STP, standard temperature and pressure. Calculate KH. See, first we have to look at the term here. Molality is given. Molality means number of moles of solute in 1 kilogram of solvent. Here it is, water is the solvent. So 0.195 moles of H2S present in 1 kilogram of water. That is the meaning. So number of moles of H2S is known to be 0.195 here. Number of moles of water 1000 by 80, 55.56 here. Standard pressure is 1.013 bar. So KH I'm going to give it in bar, so I have taken the standard pressure of 1.013 bar. In case that has the KH in atmosphere, we take it as 1 atmosphere here, right? So partial pressure of H2S equal to 1.1013 bar here, right? That's what we have taken here. Now let us see. So 1.013 equal to KH into number of moles of H2S divided into number of moles of H2S plus number of moles of water. 0.195 is the number of moles of H2S divided by 0.195 plus 55.56. Here I am not neglecting the number of moles of solute here. I am not neglecting the number of moles of solute because it's known to me and it is not negligible here. So when I am substituting the values, KH is equal to 289.64 bars here. So one thing you have to note here, the number of moles of solute plus number of moles of solvent is not taken as number of moles of solvent. Number of moles of solute is also taken into account here. KH for CO2 in water is 1.67 into 10 power 8 Pascal at 298 Kelvin. Calculate the mass of CO2 that can be dissolved in 500 ml of water at 2.5 atmosphere at 298 Kelvin. Temperature is same, pressure is changing here, right? So again, partial pressure of CO2 is equal to KH into number of moles of CO2 divided by number of moles of CO2 plus number of moles of water. So number of moles of water is 500 by 18, 500 ml here. So 500 grams, molecular mass is 18, 27.78 here. Here you look at the KH value is very high. Therefore, I can take number of moles of CO2 plus number of moles of H2 as number of moles of H2. Number of moles of solute can be neglected in the denominator here. So here, pressure exerted now is 2.5 atmosphere. Convert it into Pascal here because KH is given in Pascal. 1 atmosphere is 1.013 into 10 power 5 Pascal. So 2.5 into 1.013 into 10 power 5 Pascal is equal to 1.67 into 10 power 8, which is KH value, into number of moles of CO2 divided by number of moles of CO2 plus 27.78. I take it as 27.78 here. So 2.5 into 1.03 into 10 power 5 is equal to 1.67 into 10 power 8 into number of moles of CO2 divided by 27.78. So denominator, I neglected the value of number of moles of CO2 here. So by using this, I can find out the number of moles of CO2, which is 0.0703 moles. But here mass of CO2 is as, so multiply by molecular mass, which is 44. Molecular mass of CO2 is 44. So 0.0703 into 44, 3.093 grams of carbon dioxide is dissolved in water at 2.5 atmosphere. This is the last one. Air is a mixture of gases, contains 20% by volume of oxygen gas and 79% by volume of nitrogen gas at 298 Kelvin. Water is in equilibrium with air at a pressure of 10 atmosphere. KH for O2 and N2 at 298 Kelvin is 3.30 into 10 power 7 millimeter and 6.51 into 10 power 7 millimeter respectively. Determine the composition of the gas in water. 1 atmosphere is equal to 760 millimeter pressure here. 1 atmosphere is equal to 760 millimeter pressure here, right? So here what we are going to use, we are going to use two formula. Dalton's law of partial pressure. Partial pressure of the gas is equal to total pressure into mole fraction of the gas. Partial pressure equal to total pressure into mole fraction of the gas. That is the first one. Second one is partial pressure of the gas is equal to KH into number of moles of gas divided by number of moles of gas plus number of moles of solvent here. These are the formulas we are using here. First, I am going for the Dalton's law of partial pressure. Partial pressure is equal to total pressure into mole fraction here, right? So mole fraction of O2 and mole fraction of N2 I have to find out here. So let us say it is given 20% by mass of by volume of O2, 79% by volume of N2 here. So I can take it as number of moles of O2 is 20 divided by total is 20 plus 79. 20 by 99 is the mole fraction of oxygen. Mole fraction of N2, 79 divided by 20 plus 79. 79 by 99 is the mole fraction of N2 here. So I can find out the partial pressure. Mole fraction into total pressure. Total pressure is given as 10 atmosphere. So 10 into 20 by 99, 200 by 99 atmosphere. Partial pressure of nitrogen is 10 into 79 by 99, 790 by 99 atmosphere. So I know the partial pressure of oxygen, partial pressure of nitrogen now, right? Now in water I am coming in, right? Water 200 by 99 equal to KH into, for I'm looking for oxygen. So pressure is 200 by 99, KH into mole fraction of oxygen. KH is 3.3 into 10 power 7 given as millimeter here. So I have to convert it to atmosphere. 760 millimeter is 1 atmosphere. So I'm dividing it by 760. So 200 by 99 equal to 3.3 into 10 power 7 by 760 into mole fraction of oxygen. So by calculating, I'm finding out mole fraction of oxygen as 4.653 into 10 power minus 5 here. Next, mole fraction of nitrogen. 790 by 99 is the pressure, partial pressure of nitrogen. KH value is 6.51 into 10 power 7 in millimeters. So divided by 760 to make it into atmosphere. Into mole fraction of nitrogen here, written wrongly as oxygen. It's mole fraction of nitrogen. Change it now. Yeah. Okay. Right. So mole fraction of nitrogen, I'm calculating it is 9.316 in 10 power minus 5. Here itself we can leave in terms of mole fraction because mole fraction itself is solubility. Or you want to convert it into percentage also, you can do. So I add both the mole fraction here. Mole fraction of nitrogen plus mole fraction of oxygen. That comes to 4.653 into 10 power minus 5 plus 9.316 into 10 power minus 5. That is 13.969 into 10 power minus 5. That is the total here, right? I want to find out the mole percentage of nitrogen. That is mole 9.316 into 10 power minus 5. That is the mole fraction of nitrogen divided by total 13.969 into 10 power minus 5 into 100. That comes to 69.69%. Oxygen 4.653 into 10 power minus 5 divided by 13.969 into 10 power minus 5 into 100. That comes to 33.31 here. Thank you. Hope you found the class interesting. Next class, we will see Raoult's law and then derivation, Raoult's law for a solution containing a non-volatile solute and a volatile solvent, and for a solution containing two volatile solvents. That part we will do. If time permits, we will go for numerical based on Raoult's law. Okay, that's what I have written. Next lecture, Raoult's law for a solution containing two or more volatile solvent. Second part, solution containing a non-volatile solute and a volatile solvent. Subscribe to my channel and make the best use of videos in your preparation for board examination. Thank you very much.